right. Hello, everyone. Can you hear me? All right. My name is Vova. I'm a rock musician from Ukraine, but it's so difficult to be a musician in Ukraine that I have to promote my music on JavaScript conferences. And it's impossible to make a living, so I also have to write code. So I'm in the industry for 15 years. Out of those 11 years, I'm working in the maps industry. And for the last 6 years, I've been working at Mapbox, building mapping tools of the future. And what you need to know about Mapbox is that almost 100% of code that I write is open source. We're an open source first company. Most of the technology we release is open source. And I'm also known for creating a very simple little library called Leaflet, and also a library for interactive maps that took over the world over the last years and became an industry standard. It's now used by the world's biggest companies, and it's being taught at universities. You can see it pretty much everywhere where you see an interactive map. Like, for example, here's how it looks on Facebook. And it got so ridiculous that recently I watched a Hollywood blockbuster, The Equalizer, where 2 times Oscar winner Denzel Washington intensely stares at my JavaScript library. Yeah. So, but this library, conceptually, is very, very simple. It downloads basically square images, and you can then drag them around with a mouse. Like, it's nothing special. But for the last 6 years, I've been working on a very different kind of mapping library. It's a client-side vector rendering technology, where you don't download square images, you download raw data, like geometries of buildings, roads, their names, points of interest, etc. And you have to render them on the fly in the browser with the latest technologies like WebGL, web workers, all the recent APIs, like using the full power of the browser. And this is extremely challenging. You have to implement hundreds of different algorithms and approaches to make this experience fast for the user. So over the years, I became pretty much obsessed with performance. I try to make everything I write as fast as possible, because otherwise you can't be successful with a mapping library of this kind. Everything has to work really fast. And I also really love open source. I've been an open source contributor for many, many years, and I will continue to do so. So this obsession with performance and passion for open source combined resulted in my own approach to work, where I find a very narrow task, some algorithm or some data structure, something that I can implement and release as a separate, reusable open source library, and something that I don't have to spend too much time to maintain, so it's really reasonably small. And I make the world's fastest and simplest JavaScript library for it. And I repeat this process over and over and over and over again. And the next slides may come off as bragging, but this will help me get to my point, so it's worth it. Over the years, I created more than 100 open source projects, or maintained or actively contribute to. Those in bold are those that I created. So plenty of projects here. Most of them are pretty simple and small. Some of them are more difficult. And to give you some examples, in this vector rendering mapping library, we needed to draw polygon shapes. And to draw anything in WebGL, you have to break it down into triangles. So I created the world's fastest library for breaking down polygon shapes into triangles, which is called earcut. And it has an implementation in JavaScript and also in C++. Then we needed to make a library that generates sprite sheet layouts because we needed to pack many different images together into one texture and optimize the amount of space used as much as possible. So this became the world's fastest and smallest sprite sheet layout library, PodPack. Then we needed a way to process huge amounts of geographical spatial data on the client. So I made a library called GeoJSON-VT. In this example, it's 100 megabyte JSON file loaded directly on the client, which is sliced in a few seconds, and then you can browse it seamlessly. We needed a way to display hundreds of thousands of points on a map, such as for a heat map like this. So this is a demo with interactive display of 400,000 points. So I wrote a library for the fastest clustering library called supercluster. I'm also really into spatial indices, spatial data structures that allow you to search geometric data really fast. And I became obsessed with it, so I wrote 6 different libraries for it. We needed a way to test our mapping engine in both JavaScript version and the C++ version. 2 versions are developed in parallel. So I wrote a library for very efficient comparison of screenshots, which is now apparently used by 62,000 repositories. And the most recent example, we're working on some cool 3D features, and I needed a way to generate triangular mesh of terrain data on the client really fast. So I built this small library called Martini. So as you can see, with all those examples, they all prioritize performance over everything else. And over the years, I've built a ton of experience building super optimized code, like as fast as possible, obsessing over every line of code and making sure it's super fast. To just show you how ridiculous those performance wars can get, here's one of my favorite examples. There's a library called D3 used for data visualization. I'm sure many of you used it. Can you raise your hands? Okay, quite a few people. One of the modules in it is called D3 Delaunay for the so-called Delaunay triangulation and Voronoi diagrams. And this module is a wrapper around a library I wrote that's called Delanator, which does this kind of triangulation of point data. And let's take a simple task of triangulating 1 million points in JavaScript. A few years ago, 1 million would be quite a huge number for JavaScript, but now JavaScript is so fast that it can crunch really huge amounts of data. So this is a good benchmark. And initially, there was a library called simply Delaunay. You can find it on NPM. It's called Delaunay. And triangulating 1 million points in JavaScript took 2.5 minutes. That was too slow for many people. So someone came up with a new library called Delaunay Fast. And it was indeed faster. It was like 30% faster, which was a pretty good improvement. And they called it Delaunay Fast because it's fast. Then some other person looked at it and said, hey, I can make a faster library. And can you guess how they called it? Faster Delaunay, right. And it did the triangulation in 5 seconds, which was a massive improvement, like really huge. And I simply couldn't walk past this fun battle. So I decided to take my own stab at it, and can you guess how I named my library? Well, I had a huge temptation to call it the fastest Delaunay, but I didn't, because I would eventually get embarrassed by someone else writing a much faster library, so I called it Delanator. There are always people who are smarter and better than you and will write something better. So yeah, and my library triangulates 1 million points in 1 second. One more curious thing about it is that someone else ported this library to C++, and it's only 10% faster. So performance is very close to JavaScript 1. And also, as a learning project, I ported it to Rust, and it has the same performance. So JavaScript is so fast nowadays that if you write it very carefully and know what you're doing, you can write code that's almost as fast as native code. So you might think that, oh, you do all those really fancy and weird libraries. It probably needs some strong math education. The truth is, I dropped out of university on the 4th grade. And during my studies at the universities, I never cared about any algorithms. So what I cared about was drinking beer and playing Fallout and Baldur's Gate and doing all other nerd stuff, you know. And this is a music video of my band from that time, because I was a musician before I became web developer. I actually became web developer after I learned HTML, CSS to build a website for my band. So the biggest problem with our education system, in my opinion, especially ex-USSR countries like Ukraine, Belarus, and Russia, is that the fundamentals they give you are really great and really important, and you can get a lot out of it. But the biggest problem is that they never tell you how you use it. They don't give you practical knowledge. So you sit on those classes about algorithms and you just why do I need this? I'll better go and do something else. So after I dropped out, I started working full-time for an engineering company, and eventually I got into the mapping industry, and I had to learn all the algorithms from scratch, and all the approaches to performance, etc. So everything that I had to learn in the university, I didn't, but I learned from scratch afterwards. And I learned in an unconventional way, not an academic way. And I'll try to present you my approach to algorithms, which is simpler and maybe more practical. So why learn algorithms? Every one of you at some point faces an application or a piece of code that's really, really slow, and you have to make it faster. So there are 3 basic steps to making something faster. You first find a bottleneck, something that's slow, the exact part. And then you try to understand why it's slow. And after you understood why it's slow, you make it faster somehow. Let's look at the first part, profiling, or finding a bottleneck. Finding a bottleneck is really easy nowadays because the development tools in modern browsers are amazing. They give you so much power, like Chrome DevTools, Firefox DevTools. It's amazing how many things you can do with it. So if you see something that's slow and you measure it and you zoom into a particularly problematic area and you drill down through the JavaScript methods and you found this method called initialize style stat, for example, that's taking all the time. And now you need to decide, okay, why is it slow and what do I do about it? And now come the next two steps. And this is where algorithmic thinking and knowledge of algorithms helps you out. Because without understanding algorithms, it's really hard to understand why something is slow and how to make it faster. And we'll begin with a definition of what is slow code. Slow code is not code that's bad or using a framework that you don't like. Slow code is code that does unnecessary work, that does more things that you need for your job. A lot of examples that I'll give today are my pull request to the rollup project and its dependencies, because it's a really fantastic project. And I wanted to make it faster because we used it very extensively in production. So I'll take a look at those PRs. Here's the most classic example of unnecessary work. Throughout all the examples, you'll see the heading, like rollup 2062. This is the exact pull request that you can find on GitHub and see exactly what changed in the code. So we discovered that rollup had a problem with source maps. Like generating source maps when bundling JavaScript took a long time. And I started figuring out like what's going on, why it's slow. You look at the code and you see that to generate source maps, rollup uses a dependency called magic string, another open source library. And it gets this source map for each file that it bundles, and then it decodes this source map into a JSON object to manipulate it further. And source map looks like this. It's like a weird string with encoding of positions. And to understand why this particular part is slow, you have to look at what magic string does, like the dependency. Look there. So looking at what magic string does, it does all its magic of generating source maps, and then it takes a JSON file representing a source map and encodes it into a string. And then rollup takes the string and then it decodes it into an object to like do further things with it. And at this point, it doesn't matter what those projects do. Like you can exactly pinpoint what's wrong with this code, right? This part. You take a JSON object, convert it to a string, and then you take the string and convert it to an object back. This is completely unnecessary. Like, you can remove it, and your project will still work, and it will be faster. So it's a classic example of unnecessary work. The problem is that those two lines of code are in different projects. Like sometimes it's difficult to find this kind of thing if those two lines of code like are beside each other in one file. Sometimes they're in different files, it becomes more difficult. Sometimes they're in different projects even, so it becomes even more difficult, not obvious. So yeah, your code is a really small part of the performance picture, and often you will have to go into dependencies and try to understand what's happening there. And I met many people who think that all their performance problems can be solved by changing a framework, for example. Like, oh, my application is so slow, damn Angular, I'll rewrite everything in React and it will fly. And that's usually not what happens, right? They rewrite it in React and it's still slow and they can't understand why, so they think, maybe I should try Meteor or Vue or Svelte, whatever. But until someone really understands what's happening in those frameworks, they will never understand why it's slow. So in this example, I introduced a new method to magic string that generated a JSON file instead of encoded it into string so that I could remove those 2 lines. And source map generation got 40% faster. Just not much, but it's free, like basically removing 2 lines of code. So it was nice. Now, to dive deeper into performance, I need to talk about algorithmic complexity. And I'm sure many of you know what those things mean, like linear complexity, logarithmic, quadratic, etc. But let's just assume that you know nothing about it, and I'll try to introduce you to those concepts from scratch. Algorithmic complexity is a way to describe how performance scales with input size. And for example, if we have 1,000 input items, a constant operation, O1, is 1 operation on average. ON, linear, is 1,000 operations, 1 for each item. Quadratic, n squared, is 1 million. And n cubed is 1 billion. So let's go over in more detail. O1 is usually instant. This is something you don't have to worry about when you're thinking about performance. So things like sum of 2 elements of an array. Like no matter how big array is, this operation will be fast. Now we come to linear complexity, ON. And ON is suspicious. ON is anywhere you see loops, like for loop like this. This is suspicious. And why it's suspicious? Because any linear complexity code very easily turns into higher order complexities, and I'll show you how. So in this case, you see a loop and you know that it's a linear complexity. And now comes n quadratic, n squared. N squared is almost always terribly slow and something that you have to optimize. Every time you see 2 nested loops, it means that there's something to make faster in your code. Terribly slow, in Russian, this is also called тормозное говно. Okay, so it was obvious that this is n squared in this case because there are nested loops. But let's take, for example, here. You see a loop and you think that this is linear complexity, but you overlook that there's a index of call. And index of is also linear complexity, because to find an index of an item, you have to go through all the items in order. So this quickly becomes a quadratic complexity, and by definition, terribly slow. And it's very easy to miss if you don't know about these things. And it's easy to miss when those nested loops are together, but what if they're in different methods? It's even more harder. And this problem is so widespread that there's even a dedicated blog about it called Accidentally Quadratic. It's a serious blog which showcases many examples where in serious projects, in big established projects that were developed for like tens of years, like Chrome and React and Elasticsearch, cases where in those big projects people found accidentally quadratic performance and describes how they eliminated it. So it's an interesting problem. And then there's n cubed, which is 3 nested loops, and this usually means that you have to delete the code and write it from scratch, because it just, you can't save it. So in summary, O1 constant is instant, On is suspicious, n squared is terribly slow, тормозное говно, n cubed, you throw it out. And let's jump into a practical example. This is a D3 Delaunay library that I mentioned earlier. And one of its methods was very slow. I wanted to optimize it, but I really didn't understand what's happening in this code. It looked really complex. So, and you don't have to understand it either. Let's see how you can approach it with algorithmic thinking. You see a loop, and you think, suspicious. Then you look through the code, and you see another loop, and you say, this is terribly slow. You need to optimize it. And you start to optimize it maybe, but then you notice that there's a third line, splice, and splice is also linear. So it's n cubed, and this is what you need to do. So I had to try to write this algorithm from scratch, and it became like 3 times faster. So linear complexity can hide in many native browser methods that people don't really think about. Like many people think, oh, it's native method, so it's fast by definition. Like because there are super smart engineers who optimized it to the maximum over the last many years. But if they don't know what happens under the hood in those methods, they will keep running into performance problems. So methods like indexOf, splice, includes, reverse, every, object values, array find, sum, reduce, and this is all linear complexity. So you have to be very careful when you see method calls like this and really understand what's happening. And so far I talked about computational complexity. And I want to talk about another aspect of performance, which is memory complexity, memory footprint. And our definition of slow code is unnecessary code, and in terms of memory footprint, slow code is code that allocates more memory than you need for your code. So there are lots of native methods that are suspicious in that regard, that can produce a lot of unnecessary allocations, such as slice, concat, map, filter, and string split, which all allocate new arrays. And this can adapt to really huge performance losses. So it's very, like the currently fashionable way to write JavaScript code is like functional programming. And in this example, well, it may vary across JavaScript engines. Some engines optimize things like this, but if you think about it, what you do is you copy the array in full, then you copy it again for concat, then you create a new array with a map, and then you create a new array with a filter, and it allocates memory 4 times and throws it out immediately. So you don't need it. And this is like classic unnecessary work and makes your code slower. And this may not be noticeable in many cases, but if it's on a hot path inside of a loop that goes through like thousands of items, it may add up to huge savings. So, I know it's fashionable to talk about functional programming, immutability, reactivity, but I'm old-fashioned, so all I can think of with all those modern approaches is how many allocations this does. So this is another classic example. You do something in a function and you return two values. JavaScript doesn't support like multiple return values like some languages like Rust do. So you have to return an array, for example, or an object. And every time you do that, you allocate a new object. So here you return x and y. You only need two values, but under the hood, the engine allocates quite a big chunk of memory because it anticipates that this array, you will push items to it. So, and if you immediately destructure this and don't use this array anymore, this is unnecessary work. And here's another practical example. Source map codec is a library for, again, for source map encoding and decoding, which is used in Rollup. And before I looked at it, it looked basically like this. You took a huge string, which is source map, and you split it across semicolons, and then you go over each line and split each line into segments. And then for every segment, you decode it into an array of values, and then you do something with it. So at every point of this highlighted lines, you allocate new arrays. And this adds up to huge performance issues. So I rewrote it from scratch to have a streaming implementation where we go over each character by character, and never allocate any arrays or objects at all. So just one loop, we go character by character, and this made decoding 3 times faster. And one more big category I didn't talk about yet is logarithmic complexity. So there's constant complexity, which is like instant, and there's linear complexity, which is suspicious. Where do you think the logarithmic complexity gets? Yeah, so many people think it's somewhere in the middle, but actually it's somewhere here. Logarithmic complexity is really, really, really fast. So to give you an example, if we have 1 million objects, logarithmic algorithm will crunch it in 20 operations, which is much faster than 1 million. The most classic example of a logarithmic algorithm is binary search. Many people don't understand it, but I think conceptually it's really easy. So imagine you have some sorted array and you need to find an item in it. To find it, first you look at the middle point, and you immediately know if your item is to the left or to the right. So at each step, through one operation, you can get rid of half of the items. So you got rid of the half of the items, and you're looking at the first half. Then you look at the middle and get rid of another half. And you repeat this several times, and you found your item. So this is another practical example of pull request that I made to Rollup, which got really, really slow in one specific case of a bundle taking like 5 minutes instead of several seconds. And it turned out that in some cases where the source map was really long, it searched through it with linear search. And this is the whole change. This is the whole pull request, just a few lines of code incorporating binary search instead of linear search. And this part got 40 times faster. So algorithmic optimization is trying to reduce the complexity. Like if you have linear complexity, you try to make it logarithmic. If you have sorting complexity and log n, you try to make it linear, etc. And if you have cubic, you throw it out and write it from scratch, right? How do you do that? It's not obvious. So here's how I approach it. You have multiple operations that are really slow. They are repeatedly slow. and you need to make it faster. What do? You take the data that it processes and organize it in some way. Maybe sort it, maybe put it in some data structure, maybe put it in some object, or I don't know, doesn't matter. You organize the data somehow to make all the subsequent operations on that data much faster. And this is how you reduce complexity. So to reduce algorithmic complexity, you do more at the beginning to do less every next time. So there are plenty of data structures, and I can't possibly teach you any of the data structures on a tech talk, of course, and this is not how you learn. How you learn is you Google something, and you're faced with a problem, and you try to solve it, and you write code, and you learn. And that's how I learned all about algorithms. I just Googled a lot, and I made a lot of mistakes, and I wrote a lot of experiments. But I have a favorite data structure I can share. Can you guess what it is? My favorite data structure is a sorted array. You can't imagine how often I used it. I use it all the time in all kinds of projects. And it's really, really fast, especially if you're using typed arrays in JavaScript. They're really fast. This is a really great way to organize data and process it really fast. And there are some cool algorithms associated with sorting. So, for example, if you need to take 20 smallest items out of 1,000,000, you don't need to sort the whole array. There's an algorithm called selection, which I, of course, wrote a library for called quick select, which can do it in linear instead of n-log-n, which is much faster. Then there's this example, a library I wrote called kdbush, which is a spatial index for points, 2D points. So if you have lots of points on a plane and you need to search them really fast, like find the closest point or find points in this small area, and there are millions of points. So what's kdbush? Kdbush is essentially a fancy sorting algorithm. What it does, it sorts the whole array of points so that all the points that are on the left half are on the left, come first, and those that are on the right half come second. Then you repeat the same for each half, but this time you sort them so that all the top ones come first and then all the bottom ones come second. And you repeat this over and over until you have a kind of a data structure, but it's just a sorted array of items. And you can search through it in an instant. Another cool data structure that I use all the time is priority queue, and I love it so much that I wrote 2 libraries for it. And the last example, I'm wrapping up my talk. Here's a simple object with keys 1, 2, 3. And here's another object with keys 0, 1, 2. And you would think that they will perform the same in JavaScript. But, we used a tool for test coverage called Istanbul. Now it's also called Nick, New York. Maybe someone used it. And essentially what it does is for every line of code, for every statement in your JavaScript code, it adds instrumentation. So it means it adds statistics of how many times this particular line or statement got executed. And it saves all the statistics in an object. So on the left, 1, 2, 3, the JavaScript engines internally represent this as a hash table because they don't know what the keys will be. On the right, engines represent this as an array because it doesn't really differ from an array in any way. It's the same as simple array. So this is a pull request I made for optimizing instrumentation and test coverage, where I simply changed the index from 1, 2, 3 to 0 to 1, 0, 1, 2. And this made instrumentation 15 times faster. And this was an established tool that people have used for many years. and never noticed that there are any problems with it, and never realized that there is something that could be improved there. So people take established code for granted and think that, like much smarter people already optimize the hell out of everything I use. But that's not true. There are mistakes and there are rooms for improvement in every project, even the most established projects like React and whatever. So established code does meet best. So there is always room for improvement, and you shouldn't be afraid to dive deeper into how something works and try to make it better. Maybe become an open source contributor, but anyway, you will learn a lot. So in summary, learn how things work under the hood. Don't hesitate to dig inside frameworks. Contribute to open source because it's a great way to learn. Don't be afraid to reinvent the wheel. Simplify your code constantly, because simpler code is much easier to reason about and much easier to make fast. And practice optimization, and you learn to write fast code from the start. That's it for me. Thank you.
Thank you. We are inviting you to our seat, and we'll ask you some questions. And the first question will be easy. What's your favorite algorithm? Not that one that we use the most often, but the favorite one.
Favorite? I don't know. Binary search, probably.
Okay.
What is the best way to learn algorithms? Maybe some books or materials?
Honestly, I never read technical books at all. Like, throughout all my life, I tried reading them, but this is not how I can learn. It just doesn't work. Like, the most effective way to learn is to practice. And you mean pick some task, something that's reasonably small, that you can do it in a few days, and just start working on it. And if you don't know anything, you just Google. And yeah, learning in practice is how you learn.
Okay, the question, is there a quick way to know what algorithm would improve your performance without learning them all?
No good way. Just experimentation, and with time, the more you work with algorithms, the more you think about algorithm complexity, the more you develop a kind of intuition where you just, without knowing if there are any faster algorithms, you just feel. You have an intuition like, this is slow, this can be improved, and I will use Google to find a way.
Okay.
You write on JS, you play Metal. Is your music really fast like your algorithms?
No, my music is slow and thoughtful and melodic, and you should listen to it. It's beautiful.
Okay. How do you balance the readability of the code and the performance of it?
Usually, the fastest code is no code at all, so I make sure that the code is as simple as possible. And if it's simple, usually it's fast. And you can easily balance the two. I think it helps. Like, simplicity helps performance a lot.
Do you expect that WebAssembly will improve algorithms performance significantly, as EMD and threads particularly?
I don't think WebAssembly will help a lot with performance, because first, JavaScript is already insanely fast. Second, I experimented with WebAssembly a bit, and in my experiments, JavaScript, well-optimized JavaScript code is faster than WebAssembly, simply because of the overhead of this crossing the boundary between JavaScript and WebAssembly. And also, I think where WebAssembly shines the most is compiling existing C++ libraries and applications into the browsers, not writing something from scratch for WebAssembly.
Okay. And I suppose the last question, do we have enough algorithms for everything, or do we need more algorithms?
We need more. I came up with some of my own algorithms. You can too. It's a really fun thing. Yeah, and people always will come up with something simpler and better and faster. So yeah, there's always room for improvement, as I said.
Please choose the best question.
What one did you like the most?
I'll go with the WebAssembly one.
Okay. Thank you very much.
Thank you. I'll try to answer the other questions in Telegram. So
Yeah, there are a lot of them, so
okay.
you can definitely now go to a chat and answer everything. Okay, thank you one more time.
Thank you.